Hello, and welcome to Stanford University. I'm Craig Heller, Professor of Biology at Stanford, and I'm going to tell you today about enhancing muscle function through the extraction of heat. I'm going to tell you about some previously unrecognized avenues of heat loss from the mammalian body and how those avenues of heat loss can be exploited to enhance the exchange of heat between the body and the environment. So, you of course know Stanford as an important academic institution and a research institution, and you may not fully appreciate that it's also a very famous athletic institution. We like to call Stanford the home of champions, and everybody, of course, this is the evidence that Stanford was the winner of the NCAA Directors' Cup 27 out of the last 31 years, and that's the only period of time that the Directors' Cup was given. And that means that Stanford has excellence in a large number of sports, and of course we are therefore very concerned about the health and the performance and the conditioning of our athletes, and that's one of the reasons that we have engaged in the research I'm going to tell you about. So peak performances are exciting and winning is great. We can all agree to that. So of course, if you want to have peak performances, you have to worry about what are the components of peak performance. And those are strength, maximum power output, endurance, cognitive capacity, and skill. What you might not appreciate is the fact that all of these components of physical performance are very dependent upon temperature. Strength, your muscles stop working when they get overheated. Maximum power output, the same thing. As the body temperature rises, the ability to maintain a particular physical activity goes down. And of course that limits endurance. Now, what about cognitive capacity and skill? You'd say, well, this is the realm of the trainers and the coaches. Well, sure it is, but if you're not operating at peak cognitive ability, you're not going to be able to take advantage of all of the training and the experience you've received. So temperature is a very central factor in maintaining and continuing peak physical performance. So here's an example of how hyperthermia impairs performance. This was the first women's marathon in the Olympics. It was in Los Angeles on August 5th, 1984. And the end of the marathon was in the Coliseum. And a lasting image of that race was the Swiss competitor Gabriele Anderson-Schiess staggering the final 400 meters around the Coliseum track in an agonizing 5 minutes and 44 seconds. She waved off anybody who wanted to help her because that would have disqualified her from being a finisher. Well, we remember that Joan Benoit wins the first women's Olympic marathon. But in my mind, this particular example of the effect of hyperthermia has stayed with me all of these years. Well, history repeats itself. In the women's marathon in the Athens Olympics in 2004, Paula Radcliffe was expected to be the winner. She was the world women's marathon champion at the time. But a few kilometers before the end of the race, she had to drop out because of a borderline heat illness, heat stroke. Indeed, even if you are extremely well fit and you are a champion, temperature plays a role in your success or failure. So Paula won the New York Marathon that same year, and in 2 subsequent years, pretty amazing times. What was the difference between New York and Athens? Well, Athens on the day of that Olympic marathon was 95 degrees Fahrenheit. And the average New York temperature for those 3 marathons was 45 degrees. So ambient temperature is something that you can't do much about, and it certainly has a big effect on performance. So it's not only impairing performance that's of concern. Hyperthermia is dangerous. Here are examples of 3 athletes that died from heat stroke. And the remarkable thing is, in all 3 cases, the heat stroke occurred during practice, not during competition. And people don't always realize how close they are to heat stroke, borderline heat stroke, and can push through the early warning signs like profuse sweating, throwing up, feeling nauseous, and so forth. Well, there are a lot of individuals who cannot avoid working at very high temperatures. And here are some examples of military personnel in very hot environments. You can see the thermometer that soldier is holding is reading almost 140 degrees. And firefighters experience extremely hot conditions on a regular basis. And even when the environment is not terribly, terribly hot, still dressing in bioprotective gear, biochemical protective gear, as is common in the military, means that you are so fully insulated that you can't dissipate adequately the body heat you're producing just at rest, and you can become hyperthermic and actually go into heat stroke. So what to do about it? Well, a number of years ago, DARPA, the Defense Advanced Research Projects Agency, wanted to look into ways of improving physical fitness of the recruits that were being sent to forward deployments. So they set up a program for research to develop efficient technology for conditioning and recruits and for enhancing their performance. Major discovery that came out of this program was that the body has heat loss portals in the non-hairy skin. And that was a discovery that we had made years earlier in this lab. And interestingly enough, that research was on exactly the opposite problem. How do you rewarm people who are hypothermic? So here just shows infrared photography of a couple individuals showing that we don't just simply dissipate heat evenly over all our body surfaces. There are certain areas of the body that are extremely well adapted for the dissipation of heat. Those are in the face, they're in the palms of the hands, the soles of the feet, and in many animals they may be in the tongue, the ears, and so forth. But I'm going to tell you about the circulatory adaptations that make these locations of the body extremely effective portals for heat loss. So I said that the insight for a solution came from opposite concerns, and those opposite concerns, ironically enough, came from a good-natured bet. A colleague of ours who was an anesthesiologist, John Brock-Utney, said, "You guys think you know so much about temperature regulation. I bet you can't solve a problem we have in the post-anesthesia care unit, the PACU. The problem? Patients come into the PACU hypothermic, and as they emerge from anesthesia, it can take the nurses hours to stop them from shivering." So the insight was by my colleague, Dennis Grahn, and he said, what if we put a limb in a negative pressure environment, in a slight vacuum? That would pull blood into that limb. We could then heat that limb with a heating pad, and that warm blood would go back into the core of the body. Well, we built a silly device, and you can see here a plexiglass cylinder, and that is enclosed at one end with a wetsuit sleeve to make a seal. The vacuum pump was used to evacuate the chamber, and then a heating pad around the arm was used to heat the arm. Well, we were expecting, this is the picture of the very first device. It's something we built in the lab, pretty crude. It's amazing we were able to get permission to take it into the PACU, but with John with us, we did. And we were expecting maybe we'd increase the warming rate by 20-25% maybe. Well, the result was remarkable. First of all, the immediate observation was there were no post-anesthetic tremors. Post-anesthetic tremors is a fancy word for shivering. So the post-anesthetic tremors were completely eliminated. And then if we look at the rise in core temperature by the external auditory meatus temperature, that's the eardrum temperature, the bottom line here shows what you get if you just use warm blankets and infrared warming lights to heat up the individual. And this is the rate at which they recover, extremely slow. We were expecting to maybe improve by 20, 25, 30% maybe. But no, this is what we found. That within less than 10 minutes, the internal core temperature of these patients was normal. And that's why there was no shivering. Well, we couldn't understand how this was even possible until we realized, well, first of all, we weren't really heating up the entire body. We were heating up the core of the body. The core of the body is only about 10% of the mass. And when you are coming out of anesthesia and you're hypothermic, the blood is sequestered in that 10% of your body mass. It's not going out to the periphery, so it cannot pull heat from the environment and bring it back into the core. But instead, we were sending the heat directly into the core, and measuring the core temperature told us that we were bringing the individual back up to a normal core temperature with less than 10 minutes. So that was one answer to the quandary of how we could be so successful in rewarming. But another answer was that we had stumbled upon these portals for heat exchange, and we were just using them in reverse. These are special blood vessels in what is called the glabrous skin, the non-hairy skin, and that in the human, the glabrous skin are the palms of the hands, the soles of the feet, and the upper part of the face above the beard line. These are skin surfaces that don't have hair follicles. Okay? And if you look at the anatomy of the blood vessels in the glabrous skin, you can see that the veins are arranged in a huge network, what's called a plexus. And essentially what that is a radiator. So the blood flow to these radiators is controlled by shunts between the arteries and the veins. These are called arteriovenous anastomoses. When they're closed, then the arterial blood has to go through the high resistance capillaries. But when they open, large volumes of blood can go directly from the arteries into the veins, and those veins make up this radiator. So what we discovered is that in our experiment here, the whole arm had nothing to do with the effect. It was only the hand. So, we were using in reverse a mammalian adaptation for heat loss. So, the obvious response to that was, why not use these heat exchange portals to extract heat from the body and counter the effects of heat in muscle fatigue, to treat individuals that were hyperthermic. For example, athletes or firefighters or military personnel. So heat transfer from different body surfaces during fixed load exercise in a hot environment was what we used to explore the ability to treat hyperthermia by extracting heat from the glabrous skin. So here you can see an individual starting to do pull-ups, and after several sets of pull-ups, you see the AVAs have opened up in the face and there's lots of blood flow, bringing heat to the face. And here's a young lady who's running on a treadmill. Before she runs, her hands are cold, her face is cool, and then you can see after running, her face is lit up, her hands have lit up. other parts of the body surface have not changed. So with exercise, with the onset of hyperthermia, and here we have exercise in creating a steady rise in core temperature over this period of time. And if we measure the heat loss from different body surfaces while the core temperature is rising, you can see that most parts of the body, down here we have the upper back, the upper arm, the abdomen, the lower back, and the thigh, they're not changing at all. As the core temperature goes to very high levels, these body surfaces aren't dumping much more heat. But the face and the palm, you can see they steadily rise in the amount of heat that they are extracting from the body core and dissipating to the environment. So here's a demonstration of the capacity of the arteriovenous anastomoses and the special veins in the palms of the hands to send cool blood back to the core. So here are two experiments. In the first experiment, the individual has cooled down his hand. So he's dipped the hand in a bucket of ice water until it was really cold. And in infrared photography, anything bright is hot and anything dark is cooler. So we're going to start this film. Uh-oh. Let's see if we can play the media. Yeah. Oh. Try again. Yeah, there we go. So just look at the left-hand picture now. Now what you can see is the cool blood that's extracting, that is dumping heat into this cold hand. That cool blood is going back to the core of the body. Okay, so that was focusing on this left hand. Now let's look at what's happening in the right hand. Same thing. The cool blood is going back into the core of the body, and it is coming out to that other hand. Okay? So what you see is the heat being distributed from the part of the body which is very cold. That cool blood is distributing the benefit of that heat sink to the rest of the body. Now let's look at the hand that was heated before the filming. So here the hand is very hot, and now you can see the other hand is cool, and the warmed blood is flowing back into the core of the body, and it is then being transferred to the other hand where it's being dissipated. Okay. So this is just a demonstration of how very high levels of blood flow to these particular surfaces of the body can serve to dissipate heat to the environment, even take up heat from the environment, and as we did in the post-anesthetic care unit, and facilitate the distribution of that heat around the body. Okay, so the original concept for a device was to make a chamber that was airtight and we could draw a negative pressure, and then to insert into that chamber a heat sink, a device that could absorb heat from the palm of the hand. And here was an experiment we originally did to see how effectively we could extract heat from someone's body. So here is our research assistant, Vin Cao. He's doing pull-ups. He did 10 sets of pull-ups, I think, or maybe 12 sets, each one to muscle failure with 3-minute rests just to raise his core temperature. And then after he did these 10 or 12 sets of pull-ups, we took one of our prototypes and we experimented what was the best vacuum, what was the best temperature in order to rapidly extract that excess heat from his body. And one day, for no reason at all, after we had treated him, he went back to the pull-up bar and he did the same number of pull-ups as in his first set. We said, holy crow, what does that mean? That means that the extraction of heat was relieving the fatigue that was created by these extreme sets of anaerobic activities. So then we started cooling him after every other set of pull-ups. And when we did that, instead of this steady fatigue curve, which you'd expect, he actually plateaued. And therefore, as a result, from 1 day to 2 or 3 days later, he increased his work volume by, I don't know, we could calculate something like 20%, which is pretty remarkable. So then we continued this for 6 weeks. Our original set of experiments was 6 weeks. And during that 6 weeks, he had gone from 100 total pull-ups to 180. Now, if you go to the gym twice a week, every week, that's what you might expect, that kind of improvement in physical performance. But now, for the next 6 weeks, we cool him after every other set of pull-ups. And you can see he goes from that 180, he goes up then in the next 6 weeks to 616. That is remarkable. There are not many people who can do 616 pull-ups. And the stars here represent control days when he wasn't cooled. So you can see the gains come when he's cooled. He keeps the gains when he's not cooled, but doesn't improve. Cooling, improvement, no cooling, keep the gain, but don't get better. Well, we then wanted to see whether or not this was just a freak experiment, a freak result, or whether it was true for a larger group of subjects. So we looked for subjects who were interested in physical fitness and were willing to give it a try. And what we found was members of our Stanford wrestlers team, including our only female wrestler at the time, Patty Miranda, who went on to win Olympic bronze in Athens in 2004. And what we did with this group is we started with the cooling because we were thinking maybe we just had a priming effect. Maybe the first 6 weeks just started this process of conditioning, and it just then went to conclusion during the next 6 weeks. So we started, and these young people came in, and in 10 sets, they were doing an average of 100 pull-ups, which is pretty respectable. Okay, and then over 6 weeks, you see they increased by almost 2.5-fold. And then when they stopped cooling, they kept their gains, but they didn't get any better. So that's pretty remarkable conditioning for people who are already at pretty high levels of fitness. Well, you might ask, how does this compare to steroid effects? I'll come back to that. But this is much, much more impressive than what you would get from using performance-enhancing drugs. So at that time, the word went out to the 49ers who were nearby, and one of the 49ers was a previous Stanford tight end, Greg Clark, and he wanted to try it out. So he came over to the lab, and actually we met him in the gym, and we asked him what activity he was really good at. What did he like to do? And he said, well, dips. I can do a lot of dips. In my first set, I can do 40 dips, and then it'll be down from there, but I can do 5 sets. That's pretty much a typical workout for me. So he came into the lab, and exactly that's what he did. In his first set, he did 40 dips. Second set, only about 22, and then it kept going down. And by the 5th set, he said, I'm completely exhausted. This is a typical pattern for me. So several days later, he came back, and we cooled his palms between sets of dips. And here was his performance. So his first set was a little bit more than the previous day, but now people are standing around watching, so maybe there was a little bit of motivation there. But look at the second set. The second set, whereas it was about 21, 22 on the first day, is now about 32, 33. And the third set, similarly, almost double what it was on the previous day. No, I'm sorry, not double, because this is not starting at 0. Sorry. But you can see it's a considerable improvement. But then he said, after the 5th set, well, I'm not tired. I can do another set. 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 And he just kept on going for 9 sets. So he then came in for 4 weeks, twice a week, and here was his initial performance. Now keep in mind that this is a professional athlete at peak physical condition for his career. And then with that cooling day, he doubled his work volume. And then over the next 3 weeks, he tripled that work volume. That's pretty remarkable, taking a professional athlete who's at peak physical condition and tripling what they can do. He brought a friend, Eric Bjornsson, who was another tight end, and he wanted to try with bench press, which he liked to do. So you can see here, these are now, I think it was 6 sets of 225-pound bench press, and the first day he did 51, and then he was cooled and did 54, 57, 60, and so forth. And then he stopped cooling for a couple weeks, and you can see no continuing improvement, but then started cooling again and continued to go up. So that was pretty respectable improvement. So now what about steroids? Well, we don't work on steroids, but there are lots of studies in the literature that have looked at the effects of steroids on bench press performance. Specifically, bench press is what we looked for in the literature. And if we took all of these studies and we plotted them on the same graph relating the treatment effect with the weeks of training, these studies, totally independent studies, they all fit on one line. And what that line tells us is that the rate of improvement of the kind of conditioning that we were doing, the bench press, on performance-enhancing drugs is 1% per week in all of these studies. And you compare that to what we were getting for Greg Clark, for example, for the dips, 300% in a month, or even the performance of Greg Bjornsson here, which is much more than 1% per week. So what about non-athletes? So here we have a group of students which did an experiment with push-ups. Once again, they did 10 sets to muscle failure, 3-minute rests, with and without cooling. And this group included men and women, and we had some of our women who were doing over 800 push-ups. And they challenged me to be their age control. So they were sort of surprised when I accepted. So I was their age control. And on my 60th birthday, I did 1,000 push-ups. But this was a crossover study. So half the group started with cooling, half started with control. And then they switched. And we were able then to show that the increase in performance in terms of push-ups per day was double with cooling than it was without cooling. What about endurance? And endurance we tested in a hot room. So we had subjects, including our DARPA program manager, to walk on a treadmill uphill in a hot environment with or without one-hand Palmer cooling. And the results were, this is just a one-off study. Each one came in twice, and they either did cooling first or they did control first. Now that was randomized. And with cooling, the increase in endurance was almost 50%, so actually 48%. But for some of the younger individuals, they doubled their performance in the heat. So here was now a more formal study of performance in the heat, and the nature of the study was to come into the hot room on the treadmill, start walking, and then raise the treadmill to a particular slope that was 60% of what the individual, 60% of the slope that would lead the individual failure within an hour or around an hour. So here you can see that individual is on the treadmill. Here's heart rate, here's esophageal temperature, and you can see that without cooling, the terminal point here was about 40 some minutes, but with cooling it was roughly about 70 minutes. So what we did then for each individual is we plotted their endurance duration with cooling against their exercise duration without cooling, and you can see that there was definitely a big treatment effect. And the interesting thing is that the greater the capability of the individual at the outset, the greater the impact. And that makes sense, because the greater the capability of the individual, the more heat they're producing, and therefore the cooling had a bigger effect. One of the things that came out of this study was that we could use as our metric heart rate as well as core temperature. So core temperature is a little bit inconvenient for subjects because they have to take a thermocouple 2 feet up the nose and down to the level of the heart. That's not comfortable for many people, although it's not really too bad. But on the other hand, you get the same stop point whether you're looking at core temperature or you're looking at 90% of age-adjusted maximum heart rate. So that gives us something to use as a metric which is not as inconvenient for the subjects as esophageal temperature. So is there a conditioning effect for endurance? And here we're repeating this experiment, uphill treadmill work in the hot room till 90% of age-adjusted maximum heart rate. And we're doing it over and over again to see if there's a conditioning effect. So here is the control. The individual comes into the hot room, walks on the treadmill at a level treadmill for 5 minutes, and then the treadmill is raised to the slope that is determined to be 65% of the workload that would bring that individual to failure within an hour. Okay? So here is the typical result. They walk on the treadmill for 5 minutes, and this is what the activity, what the heart rate would expect it to be. And then the treadmill is elevated, in this case a 9% slope, and they continue to walk at 3.5 miles per hour until they reach their 90% of age-adjusted maximum heart rate. Okay? So this is a control, typical result. Here is with cooling, typical result, quite an extension in endurance. Control, control the same. Control the same. Another cooling day, no, even better. Control the same. Another cooling day, even better. Not always, but after a number of weeks, you begin to see improvement in endurance in the controls. Presumably, they are becoming more efficient at dissipating body heat through sweating. But you get even better results with continued cooling. And finally, you can see you've more than doubled what the original endurance was. So yes, you can condition for endurance for work in the heat. So what about recovery? Sometimes you can't do much about rise in core temperature during an activity, such as a fireman fighting a fire or an athlete, football player in second quarter, towards the end of the second quarter. There's not much you can do about your rise in core temperature, but then you can recover more or less rapidly. So here are individuals that we dressed in personal protective gear, which is highly insulating, like the suits a firefighter might wear. We insulated the face with balaclava, we insulated the feet with plastic bags, and then we cooled the palmar surfaces. Or we did not cool the palmar surfaces, and instead we used cold towels, which are typically seen in athletic events. So for the cool towel, we actually had to unzip the suit, so that was an added loss of body heat. But so the individual works in the heat until a core temperature of 39 degrees, and then they are just left in the heat to recover. And if no treatment is given, their core temperature continues to rise. If they are getting cold towels, there's a little bit of a decrease, not much. They're still pretty uncomfortable after 30 minutes of recovery. But if we actually withdraw heat from the hands with or without a vacuum, you can see we get a much more rapid recovery from the heat. So all I can say is that the cold towels don't do much good. They may make you feel good, but they don't do that much in terms of extracting heat from the body. So that extends now to emergency medicine, because the standard of care for treating hyperthermia in emergency medicine is to use these chemical cold packs and to place them around the neck, in the armpits, and in the groin. That's the standard of care. Okay? So what we did is we repeated the standard of care on hyperthermic individuals. The same thing, they exercise in the hot room, they stay in the hot room, and we compared if we applied the same cold packs in the standard of care locations or on the glabrous skin, the palms of the hands, the soles of the feet, and the face. Okay? And you can see here that the rate of recovery is almost double if the cold packs are put on the glabrous skin rather than the locations dictated by standard of care. So, a little bit of biochemistry. Why does heat compromise energy metabolism? Why does heat cause muscle failure? And remind you of your sophomore level biochemistry. Fuel comes into the cell as glucose, and that glucose goes through a number of steps called glycolysis to be broken down to pyruvate. And pyruvate can then be transported into the mitochondria, where it fuels the Krebs cycle and the electron transport chain and produces ATP, which is necessary for muscle contraction. Okay? Well, this very last enzyme that converts phosphoenol pyruvate to pyruvate is temperature sensitive. So if its temperature goes much above 39 degrees, well, not much, even a small amount, it becomes more likely to be inactivated. So if you look at the whole population of these enzyme molecules, more of them are inactivated as temperature goes above about 39 degrees. Okay? So if you don't have pyruvate going into the mitochondria, you can't produce ATP, and if you don't have ATP, you can't contract your muscle. So, why is this a problem, especially for anaerobic activities? And the reason is that your skeletal muscles can increase their metabolism by 40-fold or more. Huge, huge increase in energy metabolism. And of course, if you convert fuel into work, you produce heat, because all metabolism is very inefficient. So roughly about 80% is lost as heat. Well, that increase in heat production in the muscle heats, of course, the muscle. How does that heat get out of the muscle? Only in the blood. And here is the problem. The blood flow can't go up by 40-fold or more. Okay? So it's inevitable that high levels of anaerobic activity of large dynamic muscles is going to overheat the muscle. And you can reach a point where the temperature of the muscle actually kills the cells of the muscle. And that's a very dangerous condition. Okay, so what this temperature sensitivity of pyruvate kinase is a biochemical auto-protection which prevents you from cooking your own muscles, preventing you from thermal self-destruction. So one other thing I could mention with respect to the effect of heat that is part of our considerations, our work right now, and that is the phenomenon of lactate rise with exercise. So this has led to a mythology which is very commonly held that lactate causes fatigue. And that's been proven it's been disproven in a very simple experiment, and that is infusing lactate into the blood during exercise, and it doesn't produce fatigue. Okay? So we think it's more reasonable to think about the relationship between exercise and lactate is that fatigue causes the increase in lactate, not the other way around. Lactate doesn't cause fatigue. Fatigue causes the rise in lactate. And therefore, we were interested in whether the lactate threshold, the time when you begin to see an increase in lactate in the blood, is temperature sensitive. And here you can see that, yes, it is. If we start this graded increase in work level to find the lactate threshold, if we start it at a higher body temperature, the lactate threshold is lower than if the individual starts at normal body temperature. So lactate threshold is temperature sensitive, and therefore it is related to fatigue, but because of largely not just the workload, but also the temperature of the muscle. So here's an experiment which shows that it's the heat, it's the exercise which is causing the increase in lactate, not the heat directly. So here we have an experiment in which individuals are either dressed in gym wear or they are dressed in personal protective gear. And they are either kept at a cool room temperature or they are put in a hot room at 45 degrees. Okay? And then we're looking at the rise in their esophageal temperature and the rise in their blood lactate. So here we have the person in summer gear at room temperature. Here we have the person in summer gear in the hot room. And here we have the person dressed in personal protective gear in the hot room. And you can see for 5 minutes, there's really no difference. Okay, they can tolerate that perfectly well. But now they are left in the hot room or at room temperature for an hour. Those who are at normal room temperature for an hour show no significant changes in either lactate or temperature. Those individuals who are sitting in the hot room in summer attire, their sweat rate goes up, so they're able to dissipate their heat, and there's no real increase in either the lactate or their core body temperature. And then we have the individuals that are in the hot room in the PPE, but just sitting there, and you can see that the lactate doesn't go up, but the core temperature goes way up. Okay? So now what we do is we take these individuals and we put them on the treadmill for 5 minutes at a very low workload. And what you see is those individuals who have not increased their core temperature, they also don't have much of an increase in lactate during this 5-minute exercise. But the individuals who are overheated, now for that same workload, their lactate levels go way up. Okay? So this tells us that it's the temperature which is critical, not the workload. Now for a little biochemical speculation. Maybe I shouldn't go into this, but if you are a good biochemist, you would have noticed a flaw in my reasoning throughout this presentation of lactate. And that is, if I'm correct in telling you that the effect of heat is to decrease the availability of pyruvate, okay, then where does the lactate come from? Because lactate comes from pyruvate. So if you're anoxic, if you go to high altitude and you exercise, you increase the lactate production because you don't have the oxygen to run the mitochondria and produce ATP. Okay? The mitochondria need more than just fuel. They need oxygen in order to produce ATP. So what happens if you don't have enough ATP? You produce lots of lactate, okay, from the pyruvate that is coming into the mitochondria. But what I'm telling you now, if the fatigue is caused not by anoxia, but it's caused by temperature, then we don't have pyruvate. So where does the lactate come from? Well, if you back up glycolysis, okay, you're not converting phosphoenol pyruvate to pyruvate. You back up glycolysis. You back it up so that there's no longer any forward movement of these fuel molecules. So the glucose is still coming into the cell, but it has no place to go in terms of glycolysis. Well, there's another way the cell gets rid of that glucose or accommodates it, and that's by converting it to a molecule called methylglyoxal. But methylglyoxal is toxic, so the body has to get rid of it. So what it does is it breaks down the methylglyoxal to lactate. So here's a way for, even with oxygen being present, temperature can result in a rise in lactate production. So we're in the process of investigating this hypothesis now. So we call it the methylglyoxal shunt, bypass glycolysis and convert glucose into lactate. But since there's no oxidative phosphorylation, that's not resulting in an increase in ATP production. So future applications of efficient heat exchange, here are some of them. Promotion of thermal comfort in work environments. So there are many work environments, large buildings, for example, that can't be air conditioned adequately. Working in warehouses, for example. So those individuals can suffer from hyperthermia. And comfort, of course, is a concern, but also health is another issue. And that's exacerbated with emergency workers like firefighters in stressful environments. The perioperative patient temperature management, which we started on, that still is an open application. Menopausal hot flashes are, of course, of interest to many women, and this is something that possibly we can do something about. Improved quality of life for individuals with multiple sclerosis. Individuals with multiple sclerosis are terribly temperature sensitive, and what we can do is improve their quality of life by returning them to normal activities, even if the ambient temperatures are hot. Protection from heat strokes. I'm struck by the fact that I would imagine every high school in this country has a defibrillator, but how many high school students end up with atrial fibrillation? Not very many. But how many actually suffer from borderline heat strokes or frank heat strokes and therefore thermal death? Many. And yet we don't have any devices readily available in high schools for treating this easily treatable accidental condition. It's possible that migraine headaches can be modified by use of thermal exchanges and protection of better sleep. In very hot environments, sleep is difficult, but maybe if the core temperature is slightly cooled, it might facilitate sleep. So I hope in the future we'll see some of these applications come to fruition. But in the meantime, stay cool.